This is 1 billion. 1 billion is 1,000 millions. Take a look at that. You can kind of make it out there. All right. There's 1,000 millions. That's 1 billion. This is 1 billionth. To make just one, given this decimal, you would literally need 1 billion of those things just to make one. That's how small of a piece it is. 1 billionth. Could those numbers possibly have anything in common? Well, I think we're going to find out this time on Math. What's good, everyone? Ty the teacher doing the Ty the teaching. For you 8th graders, the standard for today is for you to be able to express and compare approximations of very large and very small numbers using scientific notation. And we alluded to that a bit in the intro. 1 billion being rather large, although in the grand scheme of things, 1 billion is a drop in the bucket, and very small numbers. You know those because they're decimalized and they have the TH at the end of it. So while there's not an actual physical similarity between billion and billionth, besides the first few letters, what we can do is make both of those numbers, whether they be very large or very small, much more compact. And that's what scientific notation sets to do. So first, as always, we define. Scientific notation is again a way of writing very big or very small numbers. Now, this is how the numbers will look like once you put them in scientific notation. And I don't know why that B took off, but there we are. So, we get all these things out the way and show you that this is how scientific notation looks. There's an A there and there's a B there. Remember, we're not into algebra yet, so right now, it kind of doesn't matter what these numbers are. And as a matter of fact, both of them, A and B, will be defined when I pull the lime green box down. So, although it's starting to look like algebra, and again, 8th graders, you should be able to get ready to jump in the pool there. We'll jump in feet first instead of diving in head first. So, you can imagine a number like 1 billion and a decimalized number like 1 billionth with all the zeros and all the digits in between being brought down to this is considerably smaller. So let's take a look at the process here. Now, first of all, for the B, which is an exponent, but we're not getting into exponents as a lesson because we won't be doing too much with that B. But the B can be positive or negative. Now, for big numbers, and you've got to kind of forgive me here, I picked greater than 10, and that's technically correct. Any number bigger than 10 can be put in scientific notation, or 10 or larger can be put in scientific notation. So, literally, 10 is the first number that you can put into scientific notation. It is the smallest number you can put in scientific notation with a positive exponent. I put it like that. 10 is the smallest number you can put into scientific notation with positive exponents. Now, if you kept reading, you see that for negative exponents, when the b is negative, you're dealing with small numbers. Not negative, we don't deal with any negative numbers here. And you'll see that when I go over a few of the examples on the last slide. We won't deal with any negative numbers, but the b can be negative. When it is, we're dealing with a decimal. And in this instance, a decimal is a number that is bigger than 0, but smaller than 1. And if you think about it, you can come up with a whole bunch of numbers, decimalized though they are, that are bigger than 0 and smaller than 1. And when you have that type of number, the b, and that's the exponent in scientific notation, will be negative. Now, get out of here. I wish I would have done that. Now, the a has to be greater than 1 and less than 10. And I'm going to have to learn how to write with these boxes or stop using them, but a has to be greater than 1 and less than 10. Think about it. If it's less than 1, it's going to be a decimal. It's going to have a negative exponent, and we're dealing with a different type of number. Now, this a can't be 10, and it can't be larger than 10. It can be 1, it can be 3.8, it can be 7.2, it can be 9.4, but it can't be 10, and it can't be smaller than 1. Smaller than 1? No. 10? No. Well, now why? Why? Hopefully, the explanations will make it a little bit clearer for you. But the A has to be between 1 and 9.9 repeating. All right. So, how then do we write these numbers in scientific notation? Well, it all has to do with the decimal. And I'll wait to the end here. It all has to do with the decimal on these numbers. And what I was going to wait for, but I'll say it now, every number has a decimal on it. If it's not in the middle of the number somewhere, if it's not at the beginning of the number, it is at the end of the number. The number 6 has a decimal on it at the end of 6. It's just 6.0000 repeat. So instead of writing all those zeros into infinity and beyond, we just don't write any of them or the decimal. But if you ever looked at a calculator, it does have a little dot at the end of each number. So if you have a calculator, kind of check that out. And not a calculator on your phone. They don't do that, just a regular calculator. Now, for big numbers, you're going to move the decimal to the left until it's behind the first number and in front of the second. Repeat. For a big number, and again, that's a number that's at least 10 and into infinity. You're going to move the decimal to the left until it is behind the first digit in the number and in front of the second. For small numbers, you're going to move the decimal to the right the same way. You're going to move the decimal to the right until it's behind the first non-zero number and in front of the next digit. It could be zero, but it doesn't necessarily have to be. So again, to put a number in scientific notation, you're going to take the decimal that's given on any number, and for big numbers, you're going to move that decimal to the left until it's behind the first digit of the number and in front of the second. And for very small numbers, decimal numbers, numbers between 0 and 1, you're going to move the decimal to the right the same way until it's behind the first digit, the first non-zero digit. That's kind of a thing, point of clarity here for decimals. When you move this decimal to the right, you're going to move it behind the first number in that decimal that is not zero and stop. And I've got examples here, so if it doesn't strike you now, you'll see what I'm doing in the example. Okay? So, now, the kicker is this. The number of spaces you move that decimal is the number B. I'm going to give that a second to sink in here. The number of spaces you move that decimal will be the number you put in for B. And I didn't put it on here though, but you'll see when I do the examples, the number A will be that first non-zero digit and the number right behind it with a decimal in between. And when you have that first non-zero digit and then a decimal and then the second number, that's a number that's always greater than 1 or greater, and less than 10. But, you know, have no fear here. You'll be able to see it clearly in living color in the examples. But for now, just know that the number of spaces you move the decimal will be the number you put in for B. And remember, if you move the decimal to the left, the B is positive. If you move the decimal to the right, the B is negative. I guess that's all I had there. Okay, so let's not talk about it, let's be about it. I want to start off easy, moderate, and then difficult. And let me just rip the band-aid off now. The next lesson, 8th graders, is multiplying and dividing these numbers. All 6 of the numbers that you're going to see here, you're going to be multiplying, but they will be set up already in scientific notation. And it won't be much more than adding or subtracting the B's. But another day for that. I know. We'll do that another day. I've got to go all the way back through all the grades and come back around, pull back around to the 8th graders. Today is July 22nd. So, the next time I do that could very well be in August. But later for that. So, let's start with 216. A small number, it's bigger than 10, so we can't put it in scientific notation. While scientific notation is kind of not necessary for a number this quote-unquote small, because 216 is easy to say, it's easy to grasp, it's actually 6 to the 3rd power, so we can kind of, it's 6 to the 3rd power, so we can grasp this number pretty confidently. But to show you how easy it is to put numbers in scientific notation, let's go ahead and do that. Now, remember, for big numbers, first, here, what I was going to say earlier, and I told you to wait on. Every number has a decimal. Now, when you see the decimals coming up, you'll see the decimal. But for whole numbers, you don't see the decimal. It's always at the end of the number, because we can put a row of zeros on here and we don't change the number. It's still 216. So instead of saying 216.000 blah, 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 we just don't write the decimal. You usually don't see the decimal, but there is a decimal there. I'm going to leave it there for this number. Now, again, since this is a number that's bigger than 10, this is going to be categorized as a quote-unquote big number. So we're going to move this decimal that's at the end of the number until it is behind the first digit in the number and in front of the second. Here we go. And remember to count your spaces because that's going to be your letter B. Here we go. 1, 2. So we move the decimal 2 spaces. All right. So I already know that this is going to be times 10 to the second power. And now, when the decimal is moved 2 spaces to the left, this number now becomes 2.16. Notice this number is bigger than 1 and smaller than 10. That has to be, so you can put it in scientific notation. So we have 2.16 times 10 to the second power. This is this number in scientific notation. Now, you can do the math on it. We can do it on this one. 10 to the second power. Remember, exponent says to write this number this many times and not add, multiply. 10 times 10 is 100. All right. Oh, crap. 100. And 100 times 2.16 is 216. So while it's a math problem and you can actually work it out and get the original number here, 216, this is correct. This is correct. Okay, I'll get that circle off of there. There we are. This is correct. 216 times 10 to the second power is how that, no, sorry, 2.16 times 10 to the second power. All right, now, okay, that is not a line. Let's actually make a line here. So, we have the decimal here, 364 thousandths. Remember, these are written as tenths, hundredths, thousandths. The first digit after the decimal is the tenths place, T-E-N-T-H. It's a tenths place. Then hundred, then thousand. There's no ones place after the decimal. Just isn't. The first thing is tenths, because 10 of those tenths make 1. When you're dealing with decimalized numbers, we're trying to see how many of those it takes to make 1. I think of a dime. That's 0.10 when you write it down like money. When you write it down as money, it's $0.10. Now, 10 of those make 1.00, right? Now, if you have some pennies, and some dimes, if you had 7 pennies and 4 dimes, then you have 0.47, right? That's 47 cents, 0.47. You've got 4 tenths and 7 hundredths together for 47 100ths. 47 out of 100. Now, all that being said, we don't have to worry about the nomenclature. Just wanted to read the number, and you should be able to know place value. That is a thing, which is why I was reading the number and telling you about all of that. Kind of a backwards lesson in a lesson. This number reads 364 thousandths. Now, to put it in the scientific notation, seeing that this is a number that's bigger than 0 and smaller than 1, we're going to move the decimal, which we can see, unlike 216, it wasn't in there. We can see the decimal here. We're going to move the decimal behind the first non-zero number and be done with it. So, if you see that the first non-zero number in this decimal is 3, and it's in front of it, we're just going to move this decimal 1 space. Okay? Now we've got this number, 3.64. it is between 1 and 10. 3.64 is bigger than 1, right? But it's smaller than 10. So that's the number, that's A. That's the A. 3.64. This times 10, just write it. Now, the number of spaces we move the decimal is the B. But remember, we moved it to the right, so that B is going to be negative. And we only moved it one space. No matter, I'm going to write 10 to the negative 1. And that is equal. This is the answer. 3.64 times 10 to the negative first power. All right. Fairly easy, right? Not too big of a deal. Let's do the same process with a little bigger number. All right. We got a 5-digit number here. 37,659. Now, notice as this is not a number that's between 1 and 10 or between 0 and 1, it's classified as a big number, which is at least 10. So we're going to move the decimal to the left. And remember, the number of spaces you move the decimal is the B, but in this instance, we're moving it to the left. So the B is going to be positive. So I'm just going to put times 10 here. When we get this number between 1 and 10, we're going to put it right there. When we find out how many spaces we move the decimal, that's in the back of the number, we're going to put it right here. Here we go. 1, 2, 3, ignore that, that's just a comma, 4. Now when we put the decimal here, we have 3.765, that didn't look good, 7659. 3.7659 is greater than 1. It is less than 10. Now, why couldn't we put, let's go sidebar here. We'll try to do one sidebar. Why couldn't we do 37.659? Just stop the trip short or keep going longer. But in this case, let's stop the trip short. Why can't we just stop the trip short? I'm lazy. I don't want to go all the way to the first digit of the number. Because this number can be written in scientific notation, right? Move the decimal one space, and now we've got that number again. So you might as well just go ahead and make the entire trip. All right? Now we move the decimal 1, 2, 3, 4 spaces. So just throw a 4 right on up there. Bob's your uncle. 3.7659 times 10 to the 4th power. 10 to the 4th power is a 1 and 4 zeros. That's 10,000. 10,000 times this gobbledygook just moves the decimal 4 spaces that way, and you get 37,659. The math on this is 2 because you're not computing or carrying or doing a lot. The only thing you're doing is adjusting the number, and we're working with powers here more than anything. Every time you move this decimal to the left, we've taken this number and divided it by 10. 37,659 divided by 10 is this number, 3765.9. 3765.9 divided by 10 is 376.59. 376.59 divided by 10 is 37.659. 37.659 divided by 10 is 3.7659. And same thing with the decimal, you're just multiplying by 10. Let's take a look at a moderate decimal here. Uh-oh. So what we got going here? It's a decimal. This number, believe it or not, this number is bigger than 0. It's only like this much bigger than 0, but it's bigger than 0. This is the tenths, hundreds, thousands, 10,000, 100,000, millions, 10 millions. This number is 8,041 10 millions. 8,041 10 millionths. And that millionth number, like I said in the outset with 1 billionth, you need that many of them just to make one. In this scenario with this decimal, you need 10 million of these little things to make one. And right now, we don't have 10 million of them. We're not even close. We only have 8,041 of them. But we don't have to worry about, again, we don't have to worry about nomenclature. I just want to read these numbers to you. And again, that is 8,041 10 millionths. So let's put it into scientific notation. Write times 10. And this time, we're going to multiply this number times 10 until we get it to be between 1 and 10. That is done simply by moving the decimal behind the first non-zero number. And if you don't, I mean, you still have to put it in scientific notation. So that's why you don't stop short here. So let's go ahead and move it behind the first non-zero digit. The first non-zero digit in this decimal is, of course, the number 8. So let's take the trip here. 1, 2, 3, 4. Now we moved it 4 spaces, but we moved it to the right. So this is going to be negative. So we moved it 4 spaces, but we moved to the right. So the exponent is negative 4. And now, when we moved it 4 spaces to the right, this number is now bigger than 1, 8.041, and it's smaller than 10. Of course, remember, 10 is a number we have to put into scientific notation. It's 1 times 10 to the first power. So we don't get into all of that. So let's put this number down, which is now between 1 and 10. 8.041 times 10 to the fourth power, 10 to the negative fourth power. And all this is saying is move the decimal 4 spaces that away, and you'll get back to this number, right? 1, 2, 3, 4. Right back there. All good. See, this is low math, low calculating. We're just moving by powers of 10. And literally, every time you move a number, especially with zeros are involved, there's power of 10. 6, 60, 600, 6,000, 60,000. How many 10s are there? How many 6s are there in 60? 10. How many 60s are there in 600? 10. How many 600s are there in 6,000? 10. How many 6,000s are there in 60,000? You guessed it, 10. Now, oh, wow. Look what we have here. Does that even have a number? Okay, whoa, you saw the decimal there. Kind of snuck up on you, but does this even have a number? Yes, we do. Now, this is the ones. Get used to this being the symbol for thousands. This is millions. This is billions, trillions, and quadrillions. Now, quad we know to mean 4, but that isn't 4 numbers. It's not even 4 groups of numbers. There's 1, 2, 3, 4, 5. There's 6 groups of numbers here. Where does quad come in? Somebody's wrong. Well, no. The ones place and the thousands place all the way up to 999,999 aren't millions. So they don't have ILLIONS. Seriously, these are literally the ones place and the thousands place. Millions does have illion on it. Billion is the second one. Trillion is the third one. And quadrillion is the fourth one with ILLION. That's why it's quad 4. 1, 2, 3, 4. Illion. Quadrillion. Quadrillion. So this is 84 quadrillion, 369 trillion, 732 billion, 461 million, 894,000, 768. And just so you can see it without all this junk here, remember, after millions, this is the millions. This is where that group is counting from. Okay? After billions and trillions and quadrillions. Okay? 84 quadrillion, 369 trillion, 732 billion, 461 million, 894,000, weird number compared to the other ones, 768. Nothing on that. So there we are. Now, how do we put this number into scientific notation? Just like we did the other two. We're going to move the decimal, even there's a decimal after this one, because we can say that number again, 0.000 into infinity. We're going to move this decimal to the left behind the first digit. And no, numbers don't begin with 0. This isn't 63. We don't do that. 0 is a placeholder, which means it doesn't have to be there if it's not representing a number. So, no, you won't see a 0 at the front of a number. And if you do, just erase it and never mind. Move on. So, let's count the trip here. This is going to be a long one. We'll need a passport for this one. And we head into international waters. Here we go. 1, 2, 3, just a comma, ignore it. 4, 5, 6, just a comma, ignore it. 7, 8, 9, just a comma, ignore it. 10, 11, 12, just a comma, freak out. Sorry. 13, 14, 15, 16. We move the decimal an incredible 16 spaces. Now, I'm going to just estimate right here. All right, this is going to be the last number I put in there, which means this number is going to determine whether it's going to be a 3 or 4. And remember, estimation, 0 to 4, it stays the same. 5 to 9, it goes up. So we're just going to round this up to 8.44 times 10 to the 16th power. That's an incredibly huge number. Now, these are kind of equal. I'm going to do the wavy equal sign. I just want to put all that. Would you have to put 8.43697324? I never want to sell you all short here. 461894768 times 10 to the 16th power. That's what it is. Now, this number is bigger than 1 and smaller than 10. 8.43697324618944768. That number is bigger than 1. And that number is smaller than 10. But for decency's sake, let's just go, 8.44 times 10 to the 16th. I wouldn't get on your bad side. I wouldn't read you the riot act if you estimated, if I gave you that big of a number and you just estimated. As long as the estimation was correct, I wouldn't bust your chops too much about that. Let's take a look at that decimal we had there. Boy, here we go. The only good thing about decimals is that you can see the decimal. So let's take it to the right. That means the b value, the value of the exponent, is going to be negative. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. After 17 moves of the decimal, that helped. We finally got a number between 1 and 10. We actually got, let's do it like this, at 7.38. All right, bigger than 1, smaller than 10. If you stop short, you still got zeros that you can be added to the exponent. You go too long, you got a number bigger than 10, and you need to bring that exponent down. So just move it to behind the first non-zero number with decimals here. No matter how long it is, move it behind the first non-zero number right there. Okay? And then the number of spaces we moved it is the B. We moved it 17 spaces, but we moved it 17 spaces to the right. So that's that. When we moved the 17 spaces to the right, we took a number that is so minuscule, some 100 billionth or something like that, or which 100 billion of them will make just one, and we turned it into 7 whole ones. Just think about that. If this is 100 billionth, whatever that number is, we need 100 billion of these things to make one. And now we've turned it all the way into 7. If it's a whole bunch just to make one, we've got 7.38. This number is super huge, but in the negative direction. So, so to rewrite the number as it is, you just go the opposite of right. You go back to the left, 17 spaces, and you put the decimal back where you got it from. All right. Now, again, like I said, the next lesson for 8th graders is going to be multiplying and dividing these bad boys. And I don't know if what you've been told, but it ain't great. So we'll have something like a number in scientific notation times a number in scientific notation. Or we'll have a number, that's an E, that is me losing my mind here, in scientific notation divided by, because every fraction is a division problem, a number in scientific notation. Now just think, if these numbers here that I wrote with variables are crazy, just imagine if we use these numbers, any one of these two. So, and it's another way of multiplying them without having to go through all the rigmarole. And there is such an easy thing for this that everything's dropping today, so jump scare. Uh, there's such an easy way to go about this that it makes the practice of multiplying these very, very large and very, very small numbers absolutely easier than you would think. That'll be next time. So until then, keep working. Good work today. All right. That was scientific notation, a way of condensing very, very big or very, very small numbers. 10 is the cutoff because we kind of use base 10. There's only 10 numbers in the system of math that we have. And since 10 is a double digit number, again, it's the cutoff. If you have 10, then you can put that number in scientific notation. That's the smallest number that you can put in scientific notation, but you can. And for the decimals, those are numbers that are bigger than 0, but smaller than 1. All right. Again, next one, we're going to be multiplying and dividing those bad boys, so buckle up. It's going to be a wild ride. Um, I think what I'll do for that one is just go straight into a couple of each. We'll try a couple of 3-digit numbers to multiply, and then we'll work it up to 5. Multiply and divide 3-digit numbers or so, and then work it up to 5 or 6 or 7, but maybe not much more than that. Although the process for solving them is easier than you think, especially if you got this. So if you've ever had problems with scientific notation, this lesson hopefully is going to make you able to see that you can do it. You can do it. And now we're just going to test you just a little bit more. We're going to stretch the gum a little bit and see if you can do a little bit of math with them. You don't have to worry about adding or subtracting these things, but multiplying and dividing, yes, you will have to do that. That'll be next time. Um, Since we last talked, eighth graders, I do have a TikTok channel. It's that Ty the Teacher. Nothing's on it yet. What I plan on doing with it is when the school year starts, I'm going to find a bunch of test questions and I'm going to put them on the little 1 minute or little TikTok videos just a little bit at a time. So you can work on your test taking skills and strategies. But that'll come up after the school year starts, which is just around the corner for you all. So get your vacation in now, and it's kind of hard not to vacate because it is hellaciously hot outside. Even right now at 6:15 in the morning, it is stifling hot. So 6:15 in the afternoon is just terrible. So um, I'm from the generation where we went outside all day and just drank out the hose. Somehow we made it, but I don't think I want my children out there in that heat unless they were adequately taken care of. So parents, again, any help, any questions or anything, the email I'll put in the upper left corner. You figure it out. Like to do any help? I've got. I'm thinking I'm jinxing it. Everything crossed here. Everything crossed. I've got two tutoring gigs lined up. Uh, I'm hopeful here. I'm hopeful. Uh, they're not like private tutoring sessions. They're with tutoring companies. I've always enjoyed the lower size classes, one or two or three students at the most. The state we did with the OMTC had three students at the most. It was great. They were from all over the state, and we just chopped it up, did a little math, did a little yakking, and had a lot of fun. Um, so if I do get that tutoring, one of those or both of those tutoring gigs, I don't think it's going to affect the schedule much. I make these in the morning, right when I get up. That's when I'm at my freshest. Um, yeah. So until we meet again, eighth graders and parents of eighth graders, remember that math matters because it does. See you in the next one.